Okay, so going back to our posterior, remember it's a normal distribution with parameters mu and lambda, and these are the equations. Let's clear this up by replacing the value of lambda inside the equation of mu. So we made them both only depending on phi, our parameters, and y. Okay, so let me rewrite the terms up here. This is what we have, and if we replace lambda inside mu, we have this term you can see here, right? If we further develop this a little bit, we obtain that we can cancel these numbers because this is to the -1 here, and we end up in this equation. So finally, this is our posterior, right, with these parameters. We can take a look to this term here. We can see that if we compare the mean of our posterior with the result we obtained before in the traditional linear regression setup, this is the only term that is in there that wasn't there before. Right? Is the only difference. And what is this term doing here? First of all, we can see that sigma square is bringing the uncertainty coming from the data because we assume that the data has an independent error with a variance equal to sigma square. So that part is already adding uncertainty. For example, if we are reading the measurements from a telescope, the telescope by design has its own error coming from the instrument, and that's something we cannot deal with and is part of the uncertainty we need to manage when we analyze the data. This term is the uncertainty coming from the prior, telling that, you know, before I see any data, I also have some beliefs around our parameter W. So you should take that into account, and that's part of the uncertainty also later when we are in front of data. So these two terms are combined here and are modifying the optimal value we found before in the traditional linear regression setup. You also can see that this can be seen as a regularization term because it is reducing the size of mu, in other words, reducing the size of W. And whenever we control somehow the size of a parameter, we make that model simpler. Put in another way, let's say that if W was big, meaning that the betas were big, for every small changes in the input, we would get big changes in the output. That is a very complex model. But when a model is smooth, in general, small changes in the input do not create big changes in the output. That happens when the parameters are small, closer to 0. And this is exactly what this term is doing, because it's part of the term that is decreasing the size of mu, hence decreasing the size of W. Okay, so since we already have found the posterior, now it's time to make predictions. In other words, to find the posterior predictive. The posterior predictive distribution aims to calculate the probability of any new y, and note we're using the notation y star and x star for new data points. So what would be the probability of the prediction of a new input x star given the data we already have? And as usual, what we do is like we include the parameter we need to include, in this case W, and multiply by its posterior and integrate across the domain of W. And we already know that this posterior is this normal distribution, and we also know that the probability of any output given the input and the parameters is a normal distribution centered in the linear combination of the inputs, right? It's part of the definition of the model. Note here that this design matrix is only using the inputs of the new data points, x star. We could do this for just one y or for a vector y star. Note also that our posterior does not depend on the new data inputs. It only depends on our previously seen data and our prior, but it's not using information about the position of the new inputs at all. For example, let's say that this is our training set, the blue dots, and we want to predict y star, which is the output for a given new input x star. So the idea is to build a Bayesian model, meaning the green area that represents the distribution of our predictions for any new position. And then we could predict a distribution for the output of our new input x, where the yellow line would be the mean and the green area would be the uncertainty connected to our covariance matrix in the normal distribution. So to develop this integral, it takes a lot of algebra, but the result when we integrate the product of two normal distributions are a new normal distribution. I'm going to add one video in the description where a math professor is showing the whole derivation of this result, so you can check in case you are curious about how you get to this final normal distribution. But it's not something we're going to do in this video because it takes a while, and I feel like it's kind of out of the scope of what we want to learn here. So what are these two parameters, sigma and m, of the new normal distribution? Sigma is going to be this matrix and m is going to be this matrix. Okay, still we need to see what is Vn and m here. Okay, m is this matrix, Vn is this matrix. Okay, so what I'm saying here is whenever we want to predict the value of the output of a new input given our training set, which is exactly what we want the linear regression to do, in the Bayesian setting, we are going to obtain a Gaussian distribution with these parameters. And this is the way we build each of these two parameters. In the next video, we're going to implement this in Python. In other words, we will build these matrices and we are going to be able to predict with uncertainty the output of any unseen inputs in our database.